Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nurlaila Nadira binti Muhammad Fakri from class CEEE 2224B. Today I'm going to present on Lab 1 Ece521 Microprocessor System. The question 1 asks to write a program that will store 30 into R0, copy the content of R0 into R5, and then save data 4578561 into memory location 40000030. Execute the program and explain the differences in the results. Also, discuss the addressing modes of each instruction used. This is the program for question 1. I use CAL software. The first line is immediate addressing, the second line is register addressing, the third and the fourth line is immediate addressing, and the fifth line is indirect addressing immediate offset. The first line is to store the value of 30 into R0. We will now execute the program. As you can see here, the register R0 have the value of 30. The next line is to copy the content of R0 into R5. The register R5 will have the value of 30. Why we use MOV? It is because MOV is for 8-bit and LDR is for 32-bit. R0 have the value of 30. 30 is 8-bit, so it is suitable to use MOV instead of LDR. The next line is to declare the register R1 and R2. The register R1 will have the value 40000030 and the register R2 will have the value 4578561. And we will store the value of R2 into the R1. Why we use str? It is because we need to store the value of R2 into R1, so we use str because it is from register to memory. As you can see here at the memory windows, the value of R2 is stored into the R1. We use the little endian concept. It is the least significant bit, the first stored at address 0. This is 00, we have the value of 12, at 01 we have value of 56, 02 we have value of 78, and at 03 we have the value 45. So the value of R2 successfully stored at R1. That's all for question 1. Question number 2 asks to write and execute a program that will add 20FE5690 and FE123089 and 3458971 and save the sum in register R7. Record the changes in CPSR as well. Basically, the question asks to add 3 register, which is the number that kept in the register, and save the results in register R7. We will use 3 register as R0, R1, and R2. We also need to declare R7 as 0 because we need to assume R7 is in initial condition. We will now execute the program. As you can see here, the register R0 will have the value 20FE5690. The register R1 will have the value FE123089. The register R2 will have the value 3458971 and the register R7 will have the value of 0. The next line is ADDS R7 R0 R1. R7 is the destination. We need to add the register R0 and R1. We need to add the value in register R0 and the value in register R1 and keep the results in the register R7. Why we use ADDS? It is because the question asks to record the changes in CPSR. Based on the instruction set, if we use ADD, it didn't affect the CPSR. It didn't give any effect on NZVC. If we use ADDS, it will give the effect on NZVC. So we need to use ADDS. To add the value of R0 and R1, this is the value of R0 and this is the value of R1. And this is the results of R0 and R1. We will get 11F10 Ece521. Okay, how to find the NZVC? As you can see here, there is the carry. This is 1 and this is the carry. So, C is equal to 1. How to find N? We need to use MSB. This is the MSB and this is the LSB. MSB is equal to 1. Change the value of 1 into the binary number. 1 is equal to 0001. So, look at the left side. It is 0. So, N is equal to 0. How to find Z? We need to see at the results. If the results is equal to 0, so the Z value will equal to 1. If the results is equal to 1 or have the value, it is equal to 0. So the results have the value, so the Z will equal to 0. How to find V? V is overflow. We need to see at the MSB side also. We need to add 2 and F. Change the 2 and F into the binary number and see at the third and the fourth condition. So this is 2 and this is F. 2 is 0010, F is 1111. And we will get 10001. And see at the third and the fourth condition, third and the fourth place, it is have the value of 1 at the both place. So, V is equal to 0. If at the third and the fourth place, either at one of the place is equal to 1 and another one is 0, so V is equal to 1. If at the third and the fourth place is equal to 0, V is equal to 0. So that is how to find V. So the CPSR will be N is equal to 0, C is equal to 1, Z is equal to 0, and V is equal to 0. And the value will be kept in the R7. So the next line is ADCS R7, R7, R2. Why we use ADCS? It is because based on the previous instruction, we have carry. We have 1 as our carry. So we need to use ADCS. So R7 is the destination. The previous instruction, R0 add with R1, we kept the value in R7. So we need to add the value in R7 and add with R2. And the results will be kept in the R7. So this is R7 and R2. We will get 53691E2A. Why is there 1 here? Because this is the value of C on the previous instruction. We need to use the carry here and add with the results. So, we will get N is equal to 0, C is equal to 0 because there is no carry. Z is equal to 0 because all the results have the value, and V is equal to 1. How to find V? We need to add 1, 3, and 1. Add 1, 3, and 1, change into binary number, and we will get like this. This is 1, this is 3, and this is 1. So, to find V, we need to see at the third and the fourth place. At the third and the fourth place, it have 1 and another one is 0. So, V is equal to 1. If at the third and the fourth place, it have both 1 or both 0, the value of V is equal to 0. So, the CPSR will be N is equal to 0, Z is equal to 0, C equal to 0, and V equal to 1. And the value will be kept in R7. We will get the same value in the software and manually. 5369 1E 2A. That's all for question number 2. Thank you. For question number 3, the question asks to write a program that will store 2936 FEDA in R8 and then perform the following instructions, which is ASR, arithmetic shift right, LSL, logical shift left, and ROR, rotate to the right, on the content of that register 4 times. Comment on your result. So, this is the program for question number 3. As you can see, the register R8 will have the value 2936 FEDA. The next instruction is ASR, arithmetic shift right, which is it will shift to the right for 4 times. R0 is the destination. The value of in the R8 will shift to the right within 4 times. Based on the instruction set, the Rn will shift to the right for operand 2 times within operand 2, which is operand 2 is within 4 times. It also has a note that it has sign extend for ASR. So, as you can see here, 2936 FEDA, which is the value in R8, we need to convert into the binary number. This is the binary number of 2936 FEDA. This is the before and this is the after. The below one is the after. So, this is for ASR, it has sign extend either 0 or 1, and it has carry. So, it will shift for 4 times, which is this 1, 2, 3, 4 binary number. It will 4 of them will shift to the right. It will go to the right. And for the A1010, it will be carry, which is it will go here. It will be carry. So, for the sign extend, we need to look at the MSB of 0010. If the MSB is equal to 0, so the sign extend, which I said before, it can be either 0 or 1, it will be 0 because we need to see the MSB of the first value. So the sign extend will be 0. So after it shift to the right, the result will be 2936 F0 2936 FED. For ASR, the value will be kept in the R0. As you can see here, the register R0 will have the value 02936 FED. For LSL, which is logical shift left, based on the instruction set LSL, it will shift to the left for operand times, which is for 4 times. It also has a note that it has 0 fields. So it will be like this. Convert the value of 2936 FEDA, which is this is in hexadecimal, to the binary number, and then move to the left. So, which is the initial value at here is nothing, but for LSL it say it has 0 fields, so we need to fill it with 0. So it will be 936 FEDA 0 for LSL. The value of the LSL will be kept in R1. So the register of R1 will have the value of 936 FEDA 0. And for ROR, it is rotate to the right. So, rotate to the right, we just need to rotate the value, which is the same as before, the hexadecimal 2936 FEDA, convert to the binary number, and we need to rotate to the right. So, but the last value of the binary number will go to the first value of the after. This is the before, the upper one is the before, and the downward is the after. The last value of before will be the new value of the after. It will go here. So, we will rotate to the right, and the results will be A2936 FED. For ROR instructions, the result will be kept in R2. As you can see here, the register R2 will have the value of A2936 FED. Then, it's the end of the program. That's all for question number 3. For question number 4, the question asks to write a program that will perform logical OR 6398 with 1DFE. Execute the program and comment on the results. So we will declare 6398 as R0 and 1DFE as R1. The register R0 will have 6398 and register R1 will have 1DFE. The next instruction is ORR R2 R0 R1. It will take the value of R0 and perform the logical OR with R1 and store the value into R2. So, the register R2 will have the value of 7FFE. To check if the value is correct or wrong, we will check by using the calculator. So, 6398 or 1DFE is equal to 7FFE, which is it matched with the answer. So, that's all for question number 4. Question number 5 asks to write a program that copy 12 bytes of data starting from memory locations 4004, 0000 to memory locations starting 4004, 0020. Cite manually the content of memory in 4004, 0000 until 4004, 000B to be 01, 02 and so on. Run the program and comment on the results. Based on this question, we can see at the word set manually the content of memory to be 01, 02 and so on. It is involving the repetitive, so we will use branch and loop. And what this question asks? This question asks to copy 12 bytes of data from one memory to another memory. We need to copy the data from this memory to another memory, but we can't just copy from memory to memory. We can't copy from memory to memory. So we need the help of the register. We need the help of register as a pointer. So we use R3. We need to copy from memory to register and from register to memory. So we will use 12 counter because there is 12 data. So MOV R0 #12 is to declare the number of counter. As you can see here, at register R0, it will have 0C, which stands for 12. We need to declare the old address, the starting address of the old memory as R1 and the starting address of the new memory as R2. Then R1 will have the value of 4004, 0000 and R2 will have the value of 4004, 0020. The next line is LDRB R3 R1 #1. Why we use LDRB? LDRB is for memory to register. From this memory to this register, we will use LDRB. And from the register to memory, we will use STRB. So, we will copy from the memory to register, we use LDRB, and copy from the register to memory, we use STRB. What is the #1? This line the addressing mode of this line is post-index. So, we will add one number at the memory address will move downward one place. The current location is at 40040000, and after we add with 1, it will be 40040001. And then from register R3, it will store into register R1. Sub R01 is for counter, to reduce the number of the counter. We have 12 counter. We at the command sub R01, we will reduce the number of the counter from 12 to 11 to 10 to 9, 8. It will reduce one number. CMP is also for the counter. CMP R0 #0. It will compare if the value of the counter is same or not to 0. If the value of the counter is not same to 0, it will undergo BNE ulang. So it will ulang the load and store process until the number of counter is equal to 0. If the number of the counter is equal to 0, then it will end the program. So we will execute the program. The question asks to set manually the content of memory. So, we need to set the content of the memory content in memory address manually, starting from 01 to 0C, which is equal to 12 bytes of data. So, 01, 02, 03, 04, 05, 06, 07, 08, 09, 0A, 0B, 0C. That's all for question number 5. Question number 6 asks to write a program to compare data in num into register R2. If the data is greater than 5, store the data in memory location 4002 0000. Otherwise, add the data with 60 and store it in memory location 4002 0010. Before that, set the number with value 3. Use EQU instruction. Run the program and comment on the results. Based on the question have 4 instructions, which is the value of num into R2, and the second instruction is if R2 is larger than 5, store in the memory location 4002 0000. If the R2 is less than 5, add the value with 60 and store in the memory location 4002 0010. And the fourth instruction is set the value 3 in the num. So, we need to declare R0 as 40020000 and declare R1 as 40020010. We need to declare R2 as num, which is R2 is equal to num is equal to 3. So R2 is equal to 3. Why we declare R2 with LDR? Because num is label. Label is 32-bit address, so we need to use LDR. Another example for label instead of num is data. If the question give the word data, so we need to declare with LDR. So register R2 will have the value 3. We need to declare R3 with 5 because we need to compare R2 and 5. So we will keep 5 in the register R3. Then we need to compare R2 and R3. The current value of R2 is 3 and the current value of R3 is 5. So we need to compare R2 and R3. The next instruction is BHI. BHI is used if the question asks to compare if it is greater than. So we need to use BHI. BHI is for higher. BLO is for lower. If the question asks to compare if it is lower than, so we need to use BLO. So if R2 is greater than R3, we will undergo BHI instruction. If R2 is less than R3, we will skip the BHI instruction and will go to add instruction. So R2 is 3 and R3 is 5. 3 is less than 5. So it will skip the BHI store and will go to add R2 and add with 60. So the value of register R2 will be 63 because R2 is less than R3. Then it will go to strb R2 R1, which is it will store the value of R2 into the R1. We use strb because we need to store the value of register into the memory. So the value of R2 will be stored into the R1. How to check if it is stored in the R1? We need to copy the address of R1 and paste in the memory windows. So as you can see here, this is the value of R2. Then it will go the next instruction, which is B jump. B is stand for branch. Then it will go to jump, no operation. Then it will end the program. I will give another example if the value of R2 is bigger than R3. We can change the value of num to 10 because 10 is larger than 5. So we execute the program, and as you can see here, at the command ldr r2 num, the register R2 will hold 0A because 0A is for 10. And R3 is equal to 5. And then compare if R2 is bigger than R3 or not. So R2 is higher than R3. It will go BHI store. It will go BHI store and then will perform the instruction strb R2 0, which means the value of R2 will be stored into the R0. So, we need to copy the address of R0 and paste in the memory windows. And here it is. The value of R2 is stored in the R0, which is 0A is 410. That's all from me. Thank you.